Okay, awesome. We are recording. This is chapter 7, where we'll be talking about interval sampling and sampling distributions, essentially getting to the question of how do we understand a population from a sample. And in the last few chapters, as we've explored continuous and discrete distributions, we had information about the population parameters, such as what's the proportion and the mean. However, in most instances in real life, we really don't have this type of information on the exact parameters. So we create a statistical inference based on a sample from this general population. So in this chapter, we'll discuss how to draw a representative sample and cover some of the biases that might exist when we take this sampling method. We'll also revisit some of the concepts we've previously covered with a new lens, such as the central limit theorem and distributions, and how we can use that to inform what the probability of something might be. And lastly, we'll apply all these different concepts of sampling distributions to the application of quality control, which really brings concrete value to why you should take a sample and what you can do with it and some of the caveats that might exist. And we have some students here recording with us today. So if other folks chime in at all, hope to have some conversations as we go through this. So as we progress in our semester, we'll start to dive deeper into statistical inference. Compared to just doing some exploratory analysis, we're going to try to use the data we have to test hypotheses about the samples, for example. And we need to do this from a population of data. So recall what the population is. This consists of all items of interest in a population of whatever you're looking at. This is the entire scope, whereas a sample is just a subset of the population. And why do we use this approach? Well, we have to take a sample because it would be infeasible to really measure the entire population. For example, we use survey data to understand more about the population it represents, compared to something like the census, which is taken every 10 years and is supposed to exhaustively measure every single individual in the United States, compared to a sample, which just takes a smattering of the entire population. So it's not feasible to do that because that's why it's only 10 years and it's very expensive and time consuming to do. So again, in later chapters, we'll start to apply these concepts to this concept of estimation and use it for hypothesis testing, which are based on sample information. And it's just important to note that no matter how sophisticated our analysis is, the credibility of any insight we're able to gather really depends on the quality of our input data. There's this phrase, garbage in, garbage out, that comes to my mind when I think about this. So as a primary requisite of a good sample, when I say this is a good sample, it must be representative of the population we're trying to describe. If we use a biased sample, our resulting analysis will reflect that. So that's what I mean when I say garbage in, garbage out. If you're using a sample that grossly represents the population that you're trying to measure, whatever insight that you carry from that will not represent the population you're after. So your analysis is as good as your data. And remember back to chapter 1, we briefly touched upon bias as we discussed this survivorship bias. And that analysis, to just recollect that example, it was talking about this analysis that was done on planes that returned from World War II, trying to understand where are the planes most vulnerable. And again, the sample was only taken on the planes that returned and didn't necessarily represent the larger population of aircrafts that did not return. And the result of that analysis found the most vulnerable places were the wings and these parts of the engine that didn't get hit and resulting in a plane not returning. So this is just a very concrete example of bias when it comes to sampling. So I want to think about other ways bias exists in our data, specifically for survey related data. One aspect of this that should come to mind is this selection bias in who is asked a question. This also relates to non-response bias, which occurs when only a subset of the population is actually represented. So there's some aspects of this that apply throughout any data, but specifically thinking about who's actually being collected in a sample is something to consider whenever there's analysis being done with that data. So for example, something that came to my just attention recently was looking at 311 service requests data set, which is a data set used often in New York City related analysis. And 311 is a place where anyone can call and essentially just complain about something that's going on in their area. And I use this data set to understand what are the different service requests throughout New York City. But there's some equity issues that might relate to taking a sample of service requests that are recorded on 311 in order to actually identify, hey, are parking violations more complained about in Brooklyn compared to the Bronx? So some aspect of this equity issue of thinking who actually is going to be having the time to create a service request on 311? And perhaps are we only hearing a small subset of voices very often, or is this actually representative of the population in New York City calling to complain about something? So just whenever you're creating analysis off of something, it's good to question, where's the data coming from? Is this representative of the population I'm after? So this goal of what's considered a good sample, again, at its core is we're representing the population with this sample. And how do we do this? One approach would be this simple random sample. And this method is how you ideally would remove this selection bias. Rather than necessarily calling a list of your 10 friends, this would be a random sample of observations where each observation has the same probability of being selected from the population as the rest. So one way to do this would be to randomly assign numbers to observations and then pick a sample using a random number generator. And that's essentially what we do in Python whenever we use that random or NumPy to pick a random seed. Is we're using this random generator of numbers to assign which sample we should take. But what if there was important structure we wanted to capture in this breakdown of different groups within our population? So that's where we get to this middle graphic in this slide where we have this stratified random sampling method. And this is often used by political pollsters when they want to represent different groups throughout the population. So with stratified random sampling, it's very similar where you take this random sample throughout your population, but it's stratified with different groups where so each stratum would be proportional to the relative size of the population. And then you would take your random sample from each tier, essentially, of groupings that you'd want to represent. And a cheaper version of this would be cluster sampling, which the textbook talks more about, and I don't on this slide. That's essentially trying to do the same as the stratified random sample, but rather than creating these structures of groupings, you use something like the geographic area of different population and take a sample from each. So, and that technique would be appropriate when there isn't a lot of variance between groups and the variation in the population would need to be within the groups instead. So the goal would really be to have each cluster be a mini version of the population, and you take this random sample from each group. But really, at the end of the day, we just want to make sure that you're not taking a convenience sample, which is what we show here on the right, which would inflict this bias of selecting observations that are just easiest or most convenient. So I think if you were conducting a survey on how many college students smoke cigarettes, so you go to a bar and collect some data, but rather than doing a simple random sample, which would perhaps assign each individual in that bar a random number, and then you pick from a hat, and then you go and sample from there and actually survey them. A convenient sample would be you just walk in and you talk to the first 5 people that are closest to you to the door. But there could be a chance that folks who are standing near the door were just outside to smoke a cigarette, and maybe this could inflict the skew in the results and leading to conclusions that really didn't represent the population. So let's show in Python how we would create a sample from a data frame. So here's our notebook. And I'm just going to load in some packages. Most of these we should have already seen so far, where we have pandas, some plotting, NumPy, this random generator. This is a new one, and this is for importing data sets that we'll be using for the lecture. This one is for using that square root and other mathematical symbols. Actually, sorry, this was the one that is new, not stats. We've used that one before for doing different distributions. This one is this statsmodels.api. And this is more statistics stuff. So anyway, these are our packages that we're going to use for this notebook. This is a header talking what's going to be in the notebook. But for now, we're just going to practice these different sampling methods. And there's no actual homework based off of these sampling methods. This will be section 1 of the homework. And those homework questions are more qualitative, of saying, create a sample from this population that would be representative. But if you were to use this on a real data set, these are some tools that would be helpful for you. So first, if we're ever taking a random sampling from anything or doing anything with randomly generating numbers or distributions, in order for our research to be reproducible and for someone else to be able to replicate what it is we're doing, we have to set the seed. So I always use 42, but you can set it to any arbitrary number. And this guarantees that next time we run this, we'll get the same numbers. And I found this data set from this SM package, this stats models, that I thought would be interesting just to explore a little bit, because it was a case study or an experiment that sought to understand the influence of race and gender on job application callback rates. So this was a study done for job postings in Boston and Chicago over several months, and they built up different test cases, and the researchers randomly generated resumes to go out to a job posting using different aspects of experience, education, and then randomly assigned a name that would essentially communicate the applicant's gender or race. So I thought this would be interesting just to look at if we sample from this differently. If you were to use this almost in in litigation, where you can prove that gender or race was being used to discriminate for a job application, you would need to be able to collect data and have a representative sample of the population that you're looking for. So I thought this was interesting because it's a very real life case scenario where you'd want to be able to use statistics to inform the probability that you'd get a job out of your resume, using this type of research to support that, hey, there's no discrimination going on here. But for now, we're just using this to take different samples and looking at how we want to make sure that the sample is representative of this population. So I'm just going to call this data set. So it's a little different than calling from that CSV, because this just exists in this data sets package, where they have a lot of great stuff. So if you're looking to get creative and play around with some data, they have some just nice case study data sets to look at. So I just call this resume one, and this is just the directions to this data set. So let's open it up with this head just to see what's in here. We see there's some information about the city, the industry, the job type, and then just some aspects around the different applicants. And I think these were all pretty much made up. So we shouldn't look at this too in depth, but for now, let's just take a random sample to see. So these are all the columns. If I were to ask, what's the probability that gender is male in this simple random sample of 100 participants? Let's just calculate the probability from the entire population. So again, if this was some type of litigation case and I wanted to prove something based off of the outcome of these different applications, to say, men are more likely to get the job compared to a woman, even though if they're both equally qualified, these would be some data points we'd need to gather of saying what's the probability of even having a man versus a female in this data set. So we can calculate this. So the probability of being male is about 23%. And we just did this based on our probability rules of how many were male compared to the entire data set. And now we want to create a random sample of just 100. We're not going to do anything with this. This is just to show you this syntax of taking a sample, which returns a sample of items from this object, which is this data frame. And we're making this random state of 42 so that it can be reproducible. And we're saying don't put it back. If this was a Bernoulli process where we're itemizing marbles from a jar and we put it back, that's different. This is, we're taking out the sample and not putting it back in. So just depending on what it is that you're doing, you might say replace is true, and then you could take from the population a second time. So we just want it to take without replacement. So now in this random sample, we see it's 77 to 23, and we can just do that same proportion using this probability that the sample is male, and it's just about the same as the general population. So we can say because these proportions are the same, with respect to gender breakdown, this would represent the population. And quickly, we'll just go through this stratified random sampling. If now, for instance, I wanted to make sure by each race that's represented in this population that we have a breakdown within that of what we want for a sample. So if we wanted to use this to now follow up with these different candidates that perhaps have exactly equal qualifications, and did they get the job or not, if they're all applying to the same job, this would be something that we'd want to do. So again, it seems artificial that it was exactly equal, just looking into people who are white, people who are black, and this breakdown. So it's good just to see what was the count beforehand. We don't really need this line of code. I think I was just checking to make sure to when I was looking at different columns to look by. For example, something like if we wanted to see the different resume qualities, this would be the breakdown between a category like race. And then if we wanted to group by and take a sample of this time just 10, just so we can see, we would use this stratification to say each group by race, and we wanted to apply and take a sample of that. So this would be a way to accomplish this stratified random sampling and just a simple random sample as well. And this stratification of sampling comes into importance in other aspects too, but I won't get too much into the weeds on that now. Okay, any questions? Alrighty, so back to the lecture. So we just showed how we would accomplish these different sampling tasks. But why do we even, so we tackled the samples, but why are we doing this? Why are we using these distributions now based off the sample? And again, it's because we're interested in capturing the characteristics of the population and allowing us to then use scientific theory to develop these falsifiable hypotheses around the different populations. And this hypothesis testing is soon where we're heading towards. So it's important that we cover these fundamentals of that, of what is it that we're sampling. So we make these inferences about the population on the basis of a random sample. And we used a statistic to estimate a parameter. And by statistic, we're talking about this random variable that is measurable. And the parameter is the unknown constant that we want to know more about. So for example, what if we want to know the average amount of time people in New Paltz spend hiking? Rather than asking every single person who lives in New Paltz, we instead take a simple random sample of 50 residents to gather this sample mean statistic of average time spent hiking in order to inform the distribution of the population. And although it's important to remember that there will be some variance based on how we take this random sample of residents. And we would expect slightly different point estimates if we were to take a new batch of residents and ask them. So although if we are being representative of the population, the more samples we take should get us closer to the true value of this parameter of the population. So if you're thinking about the central limit theorem, that concept is directly related here. And thinking about this point estimate of time spent hiking, this would start to look like a distribution if we started to continually take sample residence. And ideally, this sample distribution might start to look similar to our normal distribution. And this would then allow us to measure the probability using our sampling distribution of the sample mean. Any questions? All right, so this all boils down to trying to use this unbiased sample estimate to get us closer to the population parameter. I see. Okay, hi, hi Darren, welcome. Nice to have you here with the class. Feel free at any time to interrupt with questions or along the way. So we just started talking about taking different sampling methods, and now we're going to get into more details of what to do with these samples once we have them. Okay, awesome. Just seeing on the chat. So we can, as I was saying, we're going to measure the variance of our sample distribution. For example, getting back to that, what is the average time a New Paltz resident spends hiking? This might change depending on the 50 random residents that we asked. So we refer to the standard deviation of the sample mean as this standard error, because this is really measuring the variability between samples in an attempt to understand the true variability of the population. And this standard error is calculated with the following formula, where we take the standard deviation and divide it by the square root of the sample size n. And we will walk through an example of how we use this, but the purpose of having this is to measure that variance between the samples we take. So let's walk through an example. So something I've been hearing on the news lately is all about inflation and this concept of actually shrinkflation, which means that you might be paying the same for a bag of chips, but you're actually getting less chip. So as companies are trying to rectify lost profits or battle supply chain constraints, they are giving you less for the same price. So this concept of shrinkflation, I just use this in this example of thinking about how does the size or weight of products shift over time, and is this something that we can actually measure as a data point? So this is just a little case study. Consider a company's like Frito-Lay and their Doritos package of chips, claiming that each bag to weigh 16 ounces. However, there is likely to be an inconsistency due to how the chips are packaged, resulting in a standard deviation of 0.8 ounces per bag of chips that is manufactured. So what is the expected value and the standard error of the sample mean if we took a sample of 2 packages? And it's rather straightforward at this point. We would just plug in these numbers to that calculation of our formula, where we have our mean of 16, standard deviation of 0.8, and we use these as our inputs for calculating the standard error, which would result in 0.57. So we use this to understand the sample error of if we were to take another batch of Doritos, what would we expect the kind of standard deviation to look like due to just the variability in our sample. So now we can use this to start to measure some hypotheses, such as, you're concerned you're getting less chips in your bag while still paying the same price. So we can use statistics to start to calculate the probability of getting shortchanged. So for example, what is the probability that a randomly selected package is less than 15.5 ounces? So if our sample is normally distributed, which often we'll just assume it is normally distributed, then we can transform the value of X bar, which is this like sample value X, we call that X bar, into the corresponding value z given by this formula over here, where you have this x bar, which is that sample, minus the mean divided by the standard deviation, or over the number of observations square root. So that's just the standard error. And now we're plugging this into a z formula. So since the population is normally distributed, the sampling distribution of the mean, the sample mean, and that's what x bar is, technically is. X bar means this sample mean. So that is also normally distributed. These are all just assumptions we're going by, so then we can apply these rules of probability that we've learned in the last 2 chapters to use the z-score. So this figure represents what that distribution would look like, given a sample of 4 bags of chips or 4 observations, or 2 observations, or just if we took 1 bag of chips and we measured the weight of it. So using our formula, we can manually calculate the probability of seeing a 15.5 ounce bag of chips by using the mean and standard deviation, and then using a z-score table to calculate the probability. And doing all this, we can say there's a 26.6% chance that your bag of Doritos is less than 15.5 ounces, just due to the variability in the manufacturing process. And now if we wanted to calculate this over a larger sample size, we would plug that value into n.
Quick question.
Yeah.
Just so I can like know everything, what n is the population, right?
N is the number of observations you're taking.
Ah, okay. So the population would be on the x-axis in this case.
Population is really unknown of how many bags. If we were to take the true population, that would be like every bag of Doritos chips that's ever manufactured. And so the x-axis here is this weight distribution. So they should have a label on this x-axis. So on average, the bag of chips is 16 ounces, but it could go anywhere between 14 to 18.
Oh, okay. Just making sure, because I was like, wait a minute, what does n mean? Okay, I got it now.
Okay, perfect. No, definitely, I appreciate the question. So yeah, n is usually used for sample size or a number of observations taken.
Okay, and the what else is it? P is probability, and x is the what is it? It's what is x again? I'm sorry.
No worries. So, and we use x in different ways. So even in this formula, you see x bar minus mu.
Mm-hmm.
And then below, I don't know if that was the x you're referring to, the bigger x.
Yeah. Yes.
You were referring to the bigger x or the x bar?
Yeah, the bigger x.
Okay, yeah. So that's kind of using it almost in an abstract way of saying, what's the probability that the random variable x that you take is less than or equal, or just less than, there's no equal to 15.5. So I know in a lot of the homeworks, it uses the same or similar type of format. So that's just pretty much using this x to abstractly represent the probability of seeing a random value of x that's less than this value.
Okay.
But great questions. These are important to make sure we're on the same page.
Thank you.
Yeah, no worries. So, and now we'll jump to using this in Python, how to calculate, how to do this compared to using a table. But this should essentially be a review from last time when we're using the distribution to calculate the probability. But I wanted to walk through it again. So this is the same exact example we just talked through, where we would define these inputs. And I think it's always helpful just to visualize that distribution to see what it would look like. And then we can label the axes because that distribution didn't have it. So this just creates along the x-axis using all the different values that could exist, from the mean minus 3 standard deviations to the mean plus 3 standard deviations. And we just take 100 samples of this. And then this line would package each value of that x and take a normal distribution of that value from our mean and standard deviation. And then it plots all of that. So I'm going to run this. I'm going to start to see that. Just to show you what that X looks like, I'll just show the first 5 values in that. Just so you see, it's this array of values, anywhere from 3 standard deviations below 16 to 3 standard deviations above. And that's what allows us to simulate this random distribution of, given all these values of X, what would the PDF or the probability density function look like? And this just gives us the same visual that we have here. And just gives us context when we start to think about a randomly selected bag of chips being less than 15.5. This shouldn't be inches, ounces. So we can use
bag of chips.
Yeah, yeah, that'd be awesome. So yeah, we use this CDF, the cumulative density function, which just measures everything up to that point. So everything up to 15.5, which would be about this vertical line here. And we get that same value that we had there. But what the textbook also looks at is how if we increase that value of n, or the number of observations we take, how this then informs this distribution a little bit more, because now we're taking more of these samples. And that's what we account for when we take that standard deviation and divide it by the square root of how many observations we're taking. So that accounts for this standard error that exists just by the variability in how you're sampling things. And let's change this here. And this is just doing the same exact thing we showed above, but now with this square root of 2. And it's kind of interesting how it shrinks the distribution a little bit, where you have more samples that are closer to the mean. And we take the same thing, and now we have a smaller probability of seeing a bag that's less than 15.5 ounces. And essentially this is because we're a little bit more certain, because we took 2 samples rather than just 1 sample. And if you can assume what would happen once we start to take more samples, this will get even more narrow, because we're getting closer and closer to this true distribution of weights. And if the manufacturing process is consistent with this 0.8 variance, then we should start to really see, if this was a super accurate production process of something like a medical equipment where you really can't have any standard deviation, you would really want just everything to be exactly 16 ounces. But for something like this, there's probably an allowable variance that would be considered before you would say, no, this bag of chips is too light or too heavy to be distributed. So this just goes to show how the more samples you take, this standard error gets smaller. And so when we take this probability distribution, the probability gets smaller, but we can kind of be more certain that is more accurate to the true probability. So the probability goes down from, I think it was like 26, yeah, to probability being 10. So, and you would assume if we were to take more samples, again, we'd get closer to the true probability. And these are just distributions that represent how the sample mean isn't always 16, but we have a distribution that shows. So that's why the x-axis is that distribution. And now we'll go back to the lecture. So this is what most of the homework will look like from 7.2, is using a mean and standard deviation, and essentially using a lot of the same code from last class, but now having the standard error as part of the standard deviation, because we're taking these explicit sample sizes. Because a lot of the time we don't think about the sample size when we're using the entire data frame.
I have a question.
Yeah, sure.
So because this is a random sample, did you not have to set a seed for that because you already set it earlier in the notebook? Or
Yeah,
is that a question that doesn't really need you to set a seed?
yeah, I need to, I'm pretty sure, but I would need to check again. Once you set the seed, you don't really need to set it again after that. So
whenever I see like a random sample, that's when I would need to set a seed. Is that like the only question that would need that?
Yeah, I was almost redundant here when I set a random state for this sample. It's more either or, you don't really need both. So either you just set the seed once, and that's similar to if you're creating like a world in like Roblox or something, or one of those games where you set a seed and it creates your starting instantiation point. You kind of only need to do that because then it always goes back to that same starting point. I think actually if I do this where I set the seed and then give a new random state here, that this would override that other seed. So I think this is actually redundant in a way that would alter what the other seed was saying. So I think I gave you a very confusing answer. We're pretty much, in short, you just need to set the seed once if you're ever doing any type of random generations or simulations. And I didn't need to do it a second time. So once you have it once, everything should, instantiate from this seed.
And so when you're plotting, it was like plt.plot, but like changing the variable, how you had like multiple variables and you wanted to compare them, is it automatically going to change the colors? Because I remember for other graphs, we had to manually go in and change colors.
Yeah, that is another really good question. The way it's changing colors automatically is because it is plotting these all on the same axes. And before, you would need to say what color belongs to what if you aren't doing this layering of plots on the same axes. So for example, when you had to plot, different stacked bar charts, you needed to say what the colors were. But anytime if you layer plots on top of each other, it'll default sometimes to something like this, but not always. But if you want
to, Python just knows to do that.
When you have it plotting on the same axes, like here. So if I were to say make two separate subplots and have these as like two separate plot boxes, then it wouldn't know to change the colors. But I'm saying on the same axes, layer these two distributions on top of each other. And
that's that first X after the parentheses after plot, right? That's like the axis, the X axis.
Yeah, exactly.
Okay.
Yeah, excellent question. And also, if you set a label and then hit legend, it'll plot that. So if I didn't have this, it wouldn't show that.
Cool. Okay.
And maybe even just to hone that in, like if I put this part on another plot, it would make this blue, even though this was at n equals 2. It's only because it's on the same axes that it is clever and changes the color for you.
God is smart.
Only sometimes. Great questions. Okay. So
wait, before you go on, sorry.
Nice.
So if we wanted to do 3, we just have to do 3 different plots for it and change the colors of them.
If you wanted to just change that to be 3, I made this, if we wanted to have better functional programming, like I would have defined a function that defines, it would have been something like define standard error. I'd plug in the standard deviation and the value of n, because that's really what's in here. And then I would just call this function more than one time. And then I would just set that for 3. But so to answer your question, if I wanted to do for 3, I would just need to change. And we can put them all there.
Okay.
So I bring up this functional programming because rather than typing the same thing over and over again, it's better to just define a function once, use that as your building block, and then plug in new numbers and output what it is you want. But again, this isn't a coding class. It's more like just let's get what we need done. But I think it's always helpful just to show how Python makes life a little easier. So I'll leave the 3 there too, just to show. Any other questions?
No.
Okay, cool. And just wanted to talk about how this relates to the central limit theorem, because as we showed, the more samples we take, we get to this true probability distribution. And this central limit theorem states that the sum or the average of a large number of independent observations from the same underlying distribution has an approximate normal distribution that steadily improves as the number of observations increases. So as long as this value of n, or the number of observations that we're taking, is sufficiently large enough, we will start to see this normal distribution that represents the population. So this is similar to that Plinko example. When we only dropped 1 ball, we got some random value. But as we started to simulate hundreds of balls dropping, we got this truer distribution of the probability that a ball would drop in the middle. So these concepts all relate to each other. But how do we know when this sample size is large enough to be representative? And in most cases, we don't even know the true size of the population. As we were talking about before, Darren, about if we wanted to sample all bags of Doritos ever manufactured, this population would need to be very exhaustive, but we don't really know how many bags are manufactured all the time. So we need to just take a sample that's representative and large enough relative to the population size. And then the standard error of the estimator would change. And that's why we account for that standard error. So I just wanted to cover this a little bit. The textbook has a whole section on it, but we don't have any homework assigned from it, but mostly just wanted to bring this concept of finite population correction factor to your attention, where this takes that standard error and multiplies it by a correction factor, which this correction factor would account for that added precision that's gained by sampling a larger percentage of the population. So just back to that last example, as we increase the sample from 1 to 4, we are becoming more precise in our measurement of the overall population. And we can use something like this to actually measure that precision increase. So this is used when you sample without replacement from more than 5% of a finite population. So that just pretty much means that you are sampling and it's a large enough sample to say that 5% of the finite population is actually accounted for, which is a little bit fuzzy because if you don't know the actual population size, how do you know what is 5% of that? So that's why I didn't do too much homework on this, because I haven't really seen this used often in the industry. But this is needed because under these circumstances, the central limit theorem doesn't hold, and the standard error of the estimate will be too big for it to really be useful. So I bring up this concept again just to have awareness that there is this uncertainty that exists when making inferences about a larger population, and when you only sample from a very small portion of that population. So just in basic terms, the finite population correction captures the difference between sampling with replacement and then the sampling without replacement. So if this calculated value of the FPC is close to 1, it can be ignored because it pretty much is just now multiplying the standard error by 1. So that's why it can be ignored. But as the sample size falls under 5%, the value becomes somewhat insignificant. So that's why we take this 5% value. So, and this just shows the sample size, like as you take a larger sample that you're getting to multiply it by a smaller number, this correction factor, which then would say you have more precision. So that's why with this FPC being close to 1, it pretty much is ignored. But again, I just kind of wanted to cover this because the textbook talks about it, and just to bring it to your attention how this relates to other things. But really in practice, I haven't come across this too often. But I think also I haven't done a lot with taking surveys where you really have a small sample and you want to make sure it's representative. Most of the time in data science, you kind of have lots of data, and you just really need to think like, is the data you're using representative of the population and what sampling biases exist? But usually sample size is not always an issue. But sampling is definitely used. And why is any of this important? Again, it's so that we can understand the population from a sample to better gain insight into the distribution of the population. And it's used very often when issuing surveys. There's this cost effectiveness question of using the sample distribution to represent the population. It makes it more accessible to actually learn about the population without spending the dollars on asking every individual in that population. And next, we'll be talking about how this is applied to quality control, which brings together a lot of these concepts and applies it in a very practical sense. So statistical quality control applies to the business world, whether working in manufacturing, healthcare, or technology. It's pretty critical to be able to measure the quality of the products and the services provided. So using statistical quality control techniques provides us this ability to ensure that the consistent output is high quality, and then you can say the population is high quality. So pretty much by using these concepts of sampling, we can inform the quality of a population and use it to apply for this concept of quality control. So first, we'll just review a few approaches that are used for statistical quality control, and then we'll dive into how to work with it and how to calculate it. And the first is this acceptance sampling, which these are just definitions that are in the textbook as well. But this acceptance sampling is when at the completion of any production process, an inspector comes and looks at a portion of products and tries to identify if the specifications are met. If it is, then you're good. If it's not, then it's either discarded or repaired. And a main drawback to this approach is that the detection of all defective products is not guaranteed. A customer could still very well end up with a faulty product that just wasn't sampled in this portion. So compared to this acceptance sampling, which is almost like the least exhaustive approach of quality control, where you just take a little sample and say, these are good enough, let's move with everything. So this other would be this detection approach, which is a little bit more robust and probably preferred then, where this looks at the production process rather than the output itself. And the goal of this detection approach is to determine whether the production process should be adjusted or continued before a large number of defects are produced. So think also not just applications of production in a production line, where this could apply to a lot of different things like services and technology sector. So think something that's come across for me is different customer service lines, evaluating the voice of the customer as a product that was developed at a natural language processing company, where this was used to actually monitor the quality of customer service at scale, and looking across to see what are the variation in service that's provided by inspecting this customer service process and actually looking at the process of customer service in order to evaluate, is this production of customer service, is it having high quality? So I just want to bring that up to think outside of the boxes of, we're not necessarily always producing widgets and trying to measure the variation, but how this applies to wider things. Because in life, there is always variation. No two products or services are truly identical. And this variation in the quality of an end product is inevitable. but we can use statistics to measure this variation. And so there is this chance variation and then assignable variation, where chance is more random, such as the randomness of a human or machine slightly filling, the weight in those Dorito chips a little bit differently. But this chance variation is expected as long as the magnitude is tolerable with respect to the specifications. So a more troubling source of variation is this assignable variation, which is caused by a specific event or factors that can be identified or rectified or addressed. So this would look something like drift in a machine or a service that consistently causes to over or under produce the expected output. So for production, think of a machine that is consistently drifting out of alignment, causing it to overfill the product, which would be very costly for the firm. So how can we measure these variations to make sure that everything is kept under control? And if any of you are thinking about outliers, if that's starting to come to mind, that's exactly the bells that should be ringing here, is because we can start to use variance to understand what is expected and when does something go out of control where it could be considered an outlier or something that we should be concerned about. And just a little history behind when this was starting to be used in the industry. I think the first record of this control chart being used in the same way it's used today is back in the 1920s in Bell Telephone Laboratories before they became AT&T. And the lab was acquired by Nokia. Actually, I just found out in 2016. But anyway, this is the birthplace of quality control, in addition to a lot of other developments in this laboratory. But Walter Shewhart was a researcher and is often credited as the first to apply statistics to improve the quality of output. And he developed this concept of the control chart, which monitors the behavior of a production process. So at its core, this control chart looks at the average estimate of some process over time, and then compares how often does that value go above or below a control limit. So depending on the product, these upper and lower limits can vary with room for error. So an example of when you really don't have room for error would be something like a medical device that must be extremely precise and would have a very narrow limit compared to the number of chips in a Dorito bag, which could have more variation without there being risk to the quality of the product itself. And why I bring up outliers, where in general, the limits are set to 3 standard deviations from the center line. So above and below the mean, this would be the same threshold of what we would consider an outlier to be. So we can then start to apply these distributions to understand the probability. So the way we apply this is as it relates to area under the curve, and thinking about how the area under the normal curve corresponds to 3 standard deviations above and below the mean, being about 99% of all probability of this random variable coming out to be. So there's just this 1% chance that the sample estimate will fall outside of this limit. And that's why we define the same thing here of saying it's really unlikely for a value to be more than 3 standard deviations above or below. And if it does go beyond that, we are saying the probability of this existing is outside of normal and therefore is an outlier, or this 1% of a value that is very unlikely to occur, but it did occur. So we should keep this in mind once we start getting into hypothesis testing and this p-value, because it's all very related to when we talk about outliers and this distribution of values that are between 3 standard deviations above and below the mean. So in addition to keeping control of the variance to identify outliers, we also want to use this to observe any patterns that are happening within the control limits as well. Because even if you're consistently producing within the control, there could be some weird patterns going on that might indicate some other trend in the process that you wouldn't expect and would be going awry. So if you started to see some type of cyclical nature in the output pattern, that would not be expected. We're using statistics to measure the accepted level of randomness that might exist in our production. So how do we calculate this? And by calculate this, I mean, how do we construct a control chart? And the way we do it actually depends on the variable of interest and or the type of data that are available to us. So we can use this decision tree that I have here to figure out what metrics should we be considering, such as if we are looking at continuous or discrete data, where this would be comparing a continuous process, which is what we'll focus on in this class, compared to a proportion or a discrete data to say what proportion of products have a defect. So that's on this right side of the discrete data. Our class will really just be talking about this continuous side to the left. So we won't be talking about population proportions, although that could be useful and it's covered in the textbook. We won't be covering that. We'll just be talking about a continuous cycle of data, and we have a sample that is large enough where we can use this X bar chart, which monitors the central tendency of a production process. We can also use something that looks at the variability of a production process. And this essentially covers all our boxes for what we'll be doing in class, is this aspect of we have continuous data and we have a sample size that is between 1 to 11 or more than 10. And so we can use this X bar chart, which is really all we'll be doing in our class, because I don't think this is enough context. If you were to apply this in real life, you would need to do more research on it. But this is just the highlights to keep it within scope for our class, where this right side of using discrete data and having constant sample sizes, this is, if you were to be applying this, you would need to know more, is really what I'm saying. But for the purposes of our class, our goal is just to monitor some type of production process and make sure everything is under control. Okay. So we'll go through an example of this. Let's say a manufacturer produces 1 gallon jug of milk. Every 2 hours, the company samples 25 jugs and calculates the following sample mean filling weights. This is in ounces. Assume that when the machine is properly operating, the mean or mu is 128 ounces and the sigma or standard deviation is 2. And assume that filling weights follow the normal distribution. So our question might be, is the machine operating properly? To inform this, we would need to calculate what are those limits of control of the upper and lower limits. And then we would plot to see if any sample value falls outside of the control limits. And that is really just this control chart. And I wanted to bring this to our class because it ties together concepts of sampling, of distributions, of probability, and of this concept of outliers, and using that to apply it to something in real life that you might come across in the business world. So we're going to walk through this in Python, although you could really calculate all of this by hand just by using our formulas of taking the mean and multiplying it by 3 standard deviations above or below. But we're going to walk through this in Python, and this will be similar to what it looks like in class. Not in class, in homework. So we are now up to this quality control. And I found sometimes I just find interesting articles on towards data science that I want to share with the class, because this one gets into all of the different ways you would do quality control. And again, if you wanted to find this as a helpful thing that you might want to bring to work or something like that, I would recommend doing more research on it, because these are all the other scenarios you might come across. So I just wanted to bring one of the excerpts from his code quality chart guide that I have right here. And this just looks into different samples and creates this X bar and the R chart, which looks at the variability. So I'm not going to talk too much of this. I just think it's interesting how he took this and applied it in a little bit more rigor. If you were to doing quality control in real life, some of this code would be very useful. But I just took little bits to recreate what we need for class and what we need for homework. But just wanted to show you what it's based off of, where he has this mean and range, which this is the X bar chart. This is that, I think it's in this case, the R, which just looks at the ranges. So that's just another way you can control the process where we're looking at the mean. But another concept might be like, does the range between values fall within our certain control limits? So again, at the end of the day, we're just going to be looking at the mean sample. So we don't even need to worry about this R chart. And we'll be creating something similar to this in this demo right now, and also for homework. So that is the scope of our class. So our example here, where we're talking about a milk producing company, we want to know, is this machine operating properly? So we define the mean and standard deviation, and the textbook just provided, I think, about 6 different samples that were taken every 2 hours. And we are going to use this small sample to try to inform if this machine is operating properly. So our goal is to construct this X bar chart where we have a center line with the mean, and we use this to calculate the upper control limit and the lower control limit, which was defined as 3 standard deviations above and below the mean. So I created this little function that takes the input values of mean and standard deviation, as well as the list of sample means that were taken. And it simply just creates the number of observations from that list, and it will plug it in to our formula that we learned today in class about how we take it. And I forgot when I was saying just about the formula, make sure that the standard deviation is divided by the number of observations taken, or this standard error that's attributed just to the variation in our sample size. So this formula will just calculate the upper and lower and spit that back out to you to say what those limits are. And then this was inspired by the other code I showed you above that just calculates for each value in the sample. If it's above or below our control limits, we'll just say the sample value would fall out of control. So let me define that. And now I can just plug in our values of the mean, standard deviation, and the values of X. And we can see it just went through each of those 6 samples, and they're all in control. And, intuitively by eye, we could have just calculated this and then just compared, are any of these values above or below? Or we can automate that with this little function. So now we have these values, and we can plot it on a control chart where this one, I didn't have it in the other plots, but this was our canvas size, where I'm saying on this axis, create a plot and plot just those values of X, plot the upper control limit and the lower control limit. And I just made these red, but I'm going to make one purple just so we can see the difference. And then I'm also plotting a horizontal line that shows the mean. And we are just going to label it, show the legend, and make sure we have our title there. So these are those values of X. And now just by eyes, you can see that all of them are within the upper and lower control limits. Any thoughts regarding the pattern that you might see though? Because to me, I see this consistent decrease over time. Although it's within the limits, it seems it's consistently decreasing, which might lead to some other pattern that's going on that we should perhaps continue to monitor this. But for a trend to exist, you probably would need to collect more data. This could, again, just be random that this is happening. But through this process of control chart and plotting, we can say this is in control. but there might be some other stuff afoot. So let me just do one other example, and this will be similar to the homework for this chapter, where you have a manufacturer producing paint liter cans, taking a random sample of 4 every hour and measuring that, where we have our mean and standard deviation. So in the homework, you'll just need to know from the text what exactly is the mean and standard deviation. Sometimes it'll call it the expected value, but we should know that that means mean when we say expected value. I'm going to read in a data set from the textbook. And this is just from the example actually in the textbook, where they calculate all these things for you, but the homework, you'll need to calculate it yourself. So you should be able to use the function we just did above, which I'll show you. I made a different version that specifically fits what it is we're doing here. So, because in the homework, this won't be provided for you, the upper and lower control limits. You'll have to calculate that ourselves. So that's why I wanted to run through this. So we will go through in case the sample mean and lower control and upper control weren't provided. So we will do this ourselves. So the way we would calculate this X bar or sample mean is just taking all of the observations, because let's see how many samples were actually taken, because it's important that N here is 4 because we're taking 4 samples, but that we're taking 4 samples, how many times? 25 times. So it gets a little more fuzzy thinking about what's our value of N, but the value of N is consistently how many samples are you actually measuring. It doesn't matter that we took 25 of these or 100 or 1,000, we're only taking a sample of 4 in order to understand the population. But by taking that 4 over and over again, we create this distribution. So that's why N is 4, it's not 25 here. And another way just to put that concretely is that this X bar is the mean for those 4 observations. So we're not taking the mean vertically, we're taking it horizontally. And that's why this X bar just takes those 4 columns, and I have it in double brackets to say filter to these columns, and then just calculate the mean. And I have to hit axis equals 1 because by default, it does take the vertical rows, column across rows, which would be axis equal to 0. So we need to say, take the axis of 1, which recognizes that, hey, we're just taking it across these 4 columns, and we have that sample mean. So now I just entered that. So I'm going to just hit head again, and we should see our new column we just created. And we created that because we assigned, just using one equals sign, we assigned this new column name of X bar. You know, and we could have called this anything, but I chose X bar because that's the sample mean, where they called it sample mean. So I just wanted something different. If we called it the same exact thing, actually pandas would not recognize that, hey, you already have that column, and you could get into some issues when you're trying to call something and it's going to 2 separate columns. So it's good practice to make sure all your column header names are different and unique. So in this case, if I wanted to compare just to make sure that the textbook got it right, we would see like, hey, are these values equal? And we see ours has a little bit more precision with just more decimal points. But overall, just from looking at the head, it looks like about the same thing. So that's how you would calculate the mean if it wasn't given to you. So let's just plot what this looks like of what those sample means looks like. Because now we had 25 samples of this 4 observations taken. And that is what provides us this distribution of sample means. So just to take a step back, this example wasn't really a distribution that we can plot like that and really get a good insight if we wanted to do the same exact thing. If I just did x.hist, because we only have 6, there is no histogram to plot here because it's just a list. If we had this as like a matrix where we had these 6 over time over rows, then we could plot a histogram. But for now, this is just taking those statistics where this case, we now have a distribution, and that's why we can plot it. So this is that distribution, and we start to see just by eye that most of the time the sample mean is similar to the expected value of 4 liters, which would be great. You know, if we're producing this, I would be able to sleep at night knowing that most of the time the paint is exactly where we would expect it to be. And as long as I'm okay with this standard deviation that exists, you know, I could say we are fulfilling our obligation of being a high quality paint manufacturing company. We're not shortchanging and we're not losing money by giving too much paint. But we want to make sure when we define this, if we wanted to automate this process and create some type of dashboard that would continuously monitor, I'd want to set some parameters to say what's out of control here. And we can use our function to calculate the upper and lower control limits. Can we? I'm using just that same formula I had before. And I'm just foreshadowing that we can't use that same one. Simply just the way I built it was serving the purpose of that last example, where this example now we have a distribution. So it wouldn't give us the same thing because it would think each sample in that whole list is on its own, because it's thinking out of a sample of 25, not a sample of 4. So it got confused and didn't give us the right thing. So I just wanted to show you, just be careful when you're using functions that someone else designs for other uses to make sure that it actually fits the use that you are exploring. Because if not, you might need to define a new one, or really in a better world, I should have designed a better function that's more flexible to fit different needs. But, you know, it's kind of just a very simple function that did a simple thing. If I wanted to build it to be better, I should have, but didn't need to. So just out of my approach, I made another function that does exactly what it is that we wanted to do for this case. And I just called it simple upper control limit and lower control limit. And it just controls the upper and lower control limits by just outputting our simple calculation here. So you might not need a function for it. I just like creating ones if I'm going to do something more than once. And this will just return the simple thing. So it doesn't do any of the other stuff. So now I just manually input that we have 4 as our value of n. And now we can output just the upper and lower. And because the textbook already gave us that, let's just see to make sure it's the same, where we have this lower and upper. And we could even say, you know, if we wanted to use like a Boolean to say, is this equal to, you know, I can just copy and paste from here. If, you know, this number was very big or something, and I couldn't just eyeball it, we can use Python to validate that for us. And it says, this is true. That is exactly equal to that. So let's plot this again now with our upper limit and lower limit as vertical lines here. And I'm just specifying the different colors. And now we see that same distribution where most are at 4, and we have these control limits above or below. And we see these gaps in between and nothing falling outside of that gap. So we can say it's in control. And that is what the homework will look like. It'll be pretty much exactly like this. And I just have this example. If we wanted to just use what the textbook provided us, we could. And I just took those values from the same thing. If I wanted to just use the values again from the textbook, but the homework won't have it. So that's why I wanted to walk through how you would do it yourself. But this is what that control limit chart would look like. And we don't see any patterns like we did in that last one where we started that decreasing. So this looks like the perfect amount of randomness that is within control and no weird patterns emerging. So we can say everything is under control. And that is the end of the lecture for today. And we covered different aspects of creating a sample that's representative of the population, talked a bit about bias as it exists in that approach. So different procedures we can take for sampling that are representative. We talked about how we can use that to then create a sample, these metrics of statistics to inform the parameter of the population and using that standard error. And then we applied all these things to a control chart. So thank you. Thank you for joining the class. It was great to have some students here hop in and out. So I'd be happy to do more of these. Or we can be flexible with the structure of this. Maybe something later in the week to just talk through homework would be more helpful. So open to your feedback, and I will stop the recording now.